The future is here already. It's just not evenly distributed. Yet. Today's world teems with innovation. The nexus of hardware, software, and human ingenuity promises a revolution in possibilities. What does tomorrow look like? Witness Future Proof.
Ladies and gentlemen, hello and welcome back once again to Future Proof. Your host here, Eric Kavanaugh, and today I am so excited to have Dr. Saud Sadiq on the show for an organization called the Tisch MS Center. I know too much about MS, multiple sclerosis. For anyone who knows about the disease or has someone in their family or a friend who suffers from MS, you know that it's a terrible disease. And there's a lot of mystery around what causes it. But in general, to address it, most medications really just focus on mitigating the damage or slowing the progression of the disease. But what actually happens is in the brain, the immune system turns against you, and your immune system will actually eat away at what's called the myelin sheath, which is the lining around the nerves in your brain. So if you can imagine, just like we have a sheath around electrical wiring to protect the individual from getting shocked, of course, but also to really protect the signal, which is electricity running through it. Well, the same thing is true with the myelin sheath around the nerves in your brain. The sheath protects the signal so the signal can get through. And what happens with MS is your immune system attacks the myelin sheaths, and that can cause all kinds of problems depending upon where in your brain it occurs. Well, I've looked high and low all over the planet to figure out some way to help my wife deal with her MS, and we found the Tisch MS Center, and Dr. Saud Sadiq runs that operation, and they do stem cell therapy. It's an FDA-approved phase 2 program, I believe, for stem cell therapy to help patients with MS. So with that, Dr. Saud Sadiq, tell us a bit about yourself and what you're doing at the Tisch MS Center.
I thank you for inviting me, Eric. It's an honor. I run a practice, as you know, with focus on multiple sclerosis. I also direct the Tisch MS Research Center in New York, which is a research-based facility that's adjacent and in the same location. And our goal is to find the cause of MS, obviously, so that we can establish a rational pathway to the cure. And in the meantime, while we work on that overall endeavor, the idea is to try to address problems that patients with MS have. And one of them is disability that patients with secondary progressive and primary progressive forms of MS have, and try to see if we can repair or induce regeneration so they can overcome the disability. And for that part of the multiple sclerosis, there is no known FDA-approved treatment at present. So we are filling a therapeutic void.
Mm-hmm. Yeah, that's really important. And what I find so fascinating about your approach is that you use stem cells from the patient and you extract what are really called the stem cell progenitors, right? Mesenchymal stem cell progenitors from the sternum. Can you talk about these progenitors, what they actually are, and then how you're able to use them to at least theoretically help patients?
So when we started this stem cell program research in 2001, we had a problem of what to use as a source. Embryonic stem cells come with a lot of clearances and a lot of other issues, moral and otherwise. And using stem cells derived from another patient would lead to problems of rejection. So we started looking at the patient's own source of stem cells. And one area where you have stem cells plentiful is the bone marrow. So we looked at the bone marrow, and the bone marrow, 99% or so are blood stem cells, and we don't need those. But when we harvest them after a bone marrow, we discard through steps of cell purifications the blood stem cells, and then get a purified sample of what we call mesenchymal stem cells. And these mesenchymal stem cells, or MSCs, have the potential, and they're called pluripotential, sort of plural, many potential. They have potential for forming many types of tissues: heart, kidney, fat, cartilage, as well as brain type of cells. And so we go through a step where we purify the bone marrow, discard the blood stem cells, get the mesenchymal stem cells, and then we clone the mesenchymal stem cells from a patient so we get enough of a supply which we can freeze down in liquid nitrogen and use them when we need to use them. And then when we need to treat a patient, we take the mesenchymal stem cells, grow them out, and then induce them into just a brain lineage, or we call them neural progenitors. And because they are not fully formed brain cells, we call them progenitor cells because they have the potential perhaps to become myelin producing cells or other types of brain cells. So they are kind of a neural stem cell population derived from the mesenchymal stem cells. So when we say they are MSC progenitors, what we really say is MSC neural progenitors. And the reason for that is that when you're going to use them in a patient, we put them into the spinal fluid, and we do not want them to differentiate into heart cells or cartilage or bone. They would only make brain stem cells and in that environment. And we didn't want to have what's called ectopic or abnormal differentiation, which is a fancy word for saying you don't want them to develop bone tissue in brain or cartilage tissue in the CNS.
That's absolutely fascinating. And of course, what you're dealing with in any kind of situation where you're trying to help someone's brain matter is the blood-brain barrier, right? That's been one of the main hurdles for treatments to deal with something like MS, right? Can you talk about that for a second?
Yeah, so the first thing was what source of cells do we use, and we decided to go with the autologous cells, which is self-derived. Then we looked at the bone marrow, as I've just explained. Then the third issue was how do we give them? Do we give them intravascularly, intravenously? Do we just give them by mouth? Do we give them into the arteries? And how do you get across this blood-brain barrier and give it to the area that's needed? So we thought of giving it into the spinal fluid, that's called intrathecal, and that would circumvent a lot of the cells being wasted in the bloodstream and also circumventing how to get into the blood-brain barrier. So that's why we give them directly into the spinal fluid, and they can be circulated up into all the brain pathways that the spinal fluid lines. And so that's how we overcome that and also give it into the direct location where they're most needed.
Yeah, that's amazing. And you're in the phase 2 right now, and in the phase 1, according to the research that I did, there were some impressive results. So typically, especially with progressive MS patients, there's no medication that will remyelinate the myelin sheath. So there's no medication yet, at least that I've found, that can repair that damage. So you're just trying to stop the progression to prevent it from causing more damage. But can you talk about the results you saw in the phase 1 and whatever else you could talk about for phase 2? Like, what did you see in phase 1 that encouraged you?
So thank you for asking that. So I said we started this in 2001. So first we did all the characteristics, and you have to publish that, and that's what the FDA required us to do. And we did some animal work which showed some promise in repairing lesions in mice. And then we did a dosing strategy study that's called a pre-phase 1 pilot study that was based on just treating a few patients and dosing up and seeing what the tolerability was. And then we were asked by the FDA to do a phase 1 study, which we applied for. And that was to study the safety and tolerability of these cells, to see giving 3 doses for each patient. It was open label, it was not blinded, so there was a possibility of a placebo effect. And what we found was in the 20 patients we used, 10 of them were wheelchair bound and 10 were barely able to walk, but most used either a walker or a cane. So these were significantly disabled patients. And we gave 3 treatments to each patient, and all of them completed the study. There were no dropouts, and we were able to show that this treatment was tolerated well and was safe to use. And we have had no subsequent follow-up bad results like cancer or anything else happening. In addition, we found in about 14 of those 20 patients various indicators of perhaps getting improvement. So at that point, the FDA did recommend to us that we would be approved for a phase 2 study should we plan it. So the phase 2 study was designed for 50 patients It was a double-blind, placebo-controlled. So I don't judge those patients. I know who's getting what, but I can't evaluate them. There's two other neurologists. One is for adverse events. One is blinded to that, and he's another one who's evaluating these patients. And this study is started in 2018 and will finish in 2022. And we are now about at patient number 44. But remember this, each patient takes 2 years. So we've had only about 10 of those have actually crossed over into the second phase of the phase two.
Hmm. And I know just from my research on your website and reading some of these published papers that there were improvements seen in some of these patients, which again doesn't happen from traditional approaches of working with MS. So in my mind, and when we were researching this for our own family, what I realized is that stem cells provide such a positive, hopeful avenue because again, those neuroprogenitors, if you will, they can form whatever, and they tend to, so we also see stem cell in practice for cartilage, for example, for ankles and knees and things of this nature. And the research is pretty strong that shows the stem cells will go to the locations where they're needed. So they will actually identify where there is some problem with the cartilage or with the tissue and go replete that. So replenish that. And obviously we're on a long trend here. It takes a long time to do this responsibly, but in general, I think there's a lot of hope and a lot of promise in the long term for using stem cells for this reason, right?
Well, yes, but I'll be cautious. I mean, cartilage and bone and even adipose tissue is much easier to repair.
Mm-hmm.
Brain requires the scar formation. There are fibers to be made. There are not just myelin sheets, but also axons, which is the wire that the myelin wraps around. Um, and remember, the phase one was also, everybody, I mean, a critic could say that there was a placebo effect in that people, when they know they're getting stem cells, are more likely to exercise more, they're more
Right.
likely to take care of their diets. So maybe they were neglecting themselves and are now they were getting stem cells, so they did more with physical therapy, they did more with, their just attitude, eating, and so on, and worked better, and so they got better. But I mean, some of the patients who got better did have objective signs measurable by urodynamic studies in bladder function and walking speed that we think are real effects. So we are optimistic, but I'm cautious, and I think until we get the study completed in 2022, we will not be sure of who's improving. Is it all the patients? Is it a certain level of disability? Is it secondary progressive or primary progressive? There are several questions that will still need to be answered, even if we see a therapeutic signal.
Sure. And you're also doing some work with cerebral spinal fluid, CSF as it's called. Can you share anything with our audience about what your research there is focused on and what you're trying to accomplish?
Yeah, so so there is a lot. So this is the stem cell program. We have also some other divisions. One is, like I told you, we're trying to find the cause of MS and the trigger. But there's also an experimental pathology division that looks at creating new models for forms of MS that have got a bad outlook or prognosis. And one of them is primary progressive MS, in which we have succeeded in creating a new animal model and have made some insight. I haven't published that work yet, so I'm a little going to be hesitant about giving you the details. But it does involve injecting spinal fluid in certain degrees into the neck of a mouse, keeping them alive and seeing how that develops, and then being able to figure out how the pathology develops in the mouse. So it appears like the toxic factors, if you want to call it them, are present in the spinal fluid. And the second aspect of MS that we are doing some research in with spinal fluid particularly is looking at patients who have coordination difficulties, and particularly patients who have the coordination center, the cerebellum of the brain affected. So they have slurred speech. Very superficially, they look like they've just taken alcohol intoxication. They cannot walk properly. They may have strength, and they tend to sort of fall all over the place. Their hand coordination may not be perfect. So fine actions like drinking soup or doing makeup would be difficult for them, or their handwriting would deteriorate. So that's about 15% of patients can be affected with that kind of MS. And that's very disabling as well. And there's really very little therapy for that type group of patients. So for primary progressive and cerebellar disease patients, we are doing some novel experimental studies based on animal work with spinal fluid. And in the second part, what I was talking about, the shaking, the cerebellar patients, we are looking at the chemical changes that lead to that kind of disability that we can treat. And so, to give you an example of what I mean, in Parkinson's disease, they have a tremor, and if you give dopamine or dopamine agonists, you can actually correct that for a long period. So, Sinemet is like that as a treatment for Parkinson's. We are trying to find out what neurotransmitter we can give for patients with cerebellar dysfunction and MS based on our spinal fluid studies in mice taken from patients who have that type of disorder. Challenging aspects of MS that I'm quite excited about. We've made progress and we're continuing to work on that.
Yeah, that's wonderful stuff. And just to educate our audience too, early diagnosis is so important with something like MS because it's a bit of a slow creeping disease in that sense, right? And frankly, historically, doctors had a very difficult time diagnosing MS. Now you can do so with a spinal tap. But can you talk about the importance of early diagnosis and early treatment? Because the other side of the equation is that there are many different medicines used to treat MS, and you need time to be able to figure out which patients respond to which protocols, right? Not every patient responds to the same medicine the same way. And so early diagnosis and early treatment and monitoring are all very important with dealing with MS, right?
Yes. So early diagnosis, having a good history, having a good exam, and then an MRI scan. MRI technology really revolutionized the diagnostic abilities of doing MS. Spinal fluid has always been a supportive indicator, and the earlier you start treatment, the better it is to avoid disability. And in many patients with relapsing remitting MS, you can really keep them pretty frozen in time so they never develop disability. It's really when you get into primary progressive MS or where the disease is not diagnosed early or treatment is inadequate initially, that they go into a secondary progressive phase and then they are more challenging and treatment of it is more challenging. And there are many treatments available, exactly as you've said, Eric. More than I think 15 treatments have been FDA approved, but not one medicine doesn't work for everybody, and so you have to kind of figure that out, and that can take a couple of trials and maybe a couple of years to figure that out.
Mm-hmm. And quickly, I know you've also looked into artificial intelligence and machine learning as technologies to facilitate the research process. I know we're still fairly early in that process, but one nice thing about artificial intelligence and these different algorithms that we can use is once you have enough clinical data, you can let these algorithms crawl across that data and look for patterns, look for opportunities, and look for additional insights, because I think the bottom line is this is a very complex environment that you are discovering about, right? So dealing with something like MS, how it affects the brain, how it starts, how it continues, et cetera, very, very complex situation. And I'm just curious to know, what are your thoughts about the possibility that artificial intelligence and machine learning can facilitate your research going forward and hopefully expedite some of these treatments and some of these discoveries?
Yeah, so that's a great question. So looking at the cause of MS, what we've been focused on is these patients all have antibodies in the spinal fluid, and antibodies are immune cells that are produced in relation to an environmental trigger so to speak, something that shouldn't be there, like an autoimmune attack. So once you get a trigger effect, or let's say the bacteria infects you, you make antibodies to the bacteria. Now, recently, COVID is up there. So once you get a COVID infection, what they look for evidence that you've had a COVID infection, they look for antibodies to COVID. And if you have antibodies, you can say you're infected with COVID. So in MS, patients get antibodies in their spinal fluid, but there is no known trigger. We don't know what the COVID of MS is or what the cause is. And so we have been looking at taking the antibodies, making single cells from each of the B cells that make antibodies, and taking their DNA and putting it as a blueprint and we have several thousands of patients. We have antibodies that we have sequenced, and we've got like a sequence, like a blueprint, if you know, ABCD type of thing, where on many different sequences that we have, and to try to figure out a pattern that is consistently seen would take a lot of time for us. And what we have done is we have now started partnering with Deloitte and doing AI to figure out these thousands of sequences to see what patterns are recurring. And so far, actually, already we have got identified about 6 different patterns, and that's actually now going to be our blueprint for adding more data and narrowing out, and then try to figure out, and maybe it'll point to a direction that we would look at, which would have taken us years to do, and we could do it in 6 months or so using AI.
Wow, that's fantastic stuff. And folks can hop online to tishms.org, right? That's TISCHMS.org to learn about more. And are there any ways that people can help? Are there any fundraisers you guys do that we can point people to so they can help out the cause with MS as well?
Yeah, so all our research is either through the MS Society, or we ask for donations, and patients are probably the majority of donations are funded by patients or relatives of patients. And that has been a critical support for us. And the pace of research is directly dependent on the amount of financial strength you have. So, and the faster, it's like the oil that drives the car. The more we can get, the better we do. Or the electric car, if you want to use electricity.
Right.
All right. But thank you for that. And that's been our main hindrance is the lack of funding, always. And so we have to make choices.
Yeah, well, I just want to say thank you very much, Dr. Sadiq. There are not too many people really focused on helping patients with progressive MS. It's a shame to see, but I think in some regards, patients with progressive MS feel like the medical industry has kind of left them behind. In fact, it used to be not that long ago that if you were diagnosed with progressive MS, you wouldn't even get help from insurance companies. I think all that has changed, but I just want to say thank you from our family and from all the families that you work with for the work that you're doing, because I think it's absolutely wonderful, and we wish you all the best.
Eric, thank you so much, and you're very kind.
Okay, folks, hop online to tishms.org. That's TISCHMS.org for more information. And this has been another episode of Future Proof.
So what is the point here? What are we trying to do? Really, we're trying to educate our audience about most of the really interesting, compelling technologies that are redefining the world around us. So we're going to talk about software, hardware, and really human ingenuity combined to change the world, to create these powerful tools for business and for life. And so this is going to be broadcasting on television all around the country later on this summer. You, my friends, are part of our virtual studio audience. So feel free to ask a question, and we'll work you into the show. So moving right along here, I'm really trying to recreate for the world what Carl Sagan did for me. For those of you who don't remember, Carl Sagan had this fantastic show years ago in which he talked about billions and billions of stars. And he would just really get into the details of science. And Carl Sagan made science fun and interesting. And I'm here to tell you, the man changed my life. He absolutely did. I just got chills thinking about it. It was so cool. It just opened my mind to the world of science and exploration and space and discovery and all this stuff. And I think to myself, over the years, I've done all these radio shows and TV programs, etc. And I want to help recreate something like that. And even though there is no Carl Sagan today, there's no one who fills that void, there are really thousands of people who fill that void. And there are people at all sorts of different companies around this country and around the world, quite frankly, who are working with data, who are working with analytics, who are building these new solutions that drive our economy, things like 5G, for example. All this cool stuff is being generated by really interesting people. And our job at Future Proof is to find those people and to have them present and share their ideas with you on the show.
Part of what I do in my world is, my background is in distributed computing, and that I've been doing this since I was in university in the 1990s. And distributed computing has always offered a really interesting view of the future, but for the right reasons. Centralizing things or versus distributing things. Well, this is where we're heading in general. It's already a thing. But let's focus on edge computing. What is edge computing beyond the buzzword? Let me give you a simple example. And I think this will drive home a really important point. So let's say that you went to you heard about a great cafe, we call it the App Cafe. You go with a friend and you read the menu. Wow, this looks like amazing food. The server's there, takes your order. Wow, let's get some food. Well, all of a sudden you see your server driving off in a car or a delivery van. And you're like, what is going on here? Why is this person leaving? Well, the reason they're leaving is because the kitchen for that cafe is actually farther away. And that's Cloud Kitchen. And so the server is then delivering the order to the kitchen. The kitchen then spends the time to make it and then puts it into the delivery van and sends back with the wait staff. And here's your food. Well, that's kind of ridiculous. But even more ridiculous is like, wait a minute, I ordered soup, not a salad. Oh, no problem. I'll go get it. So that's really a bummer. If you actually went to a restaurant or a cafe and you saw this happening, I'll bet you're probably not going to leave a very good Yelp review because, there's lots of reasons. First of all, your food may be cold. Second of all, the service is not going to be that speedy. If someone's driving across town, who knows what's going to happen? Traffic, potholes, they get into an accident, what have you. So this is just not a really good way to run a restaurant. Now, formal, this is right off of Wikipedia. You can't get any better than that. Edge computing, distributed computing, yay. But it's this whole thing about computation and data storage. And the key here is closer to the location where it's needed. And that, I think, makes sense in a lot of people's minds because, going back to our restaurant analogy, edge computing is like having a kitchen in every restaurant, which sounds really obvious. But we don't build our computer networks and how we do applications like that right now. We have built out an enormous application infrastructure that is based on the idea that someone takes your order, gets into a car, and goes to the kitchen, not attached to the restaurant. Let's talk about why. What's driving this new future? Why was this never a thing in the beginning? In the beginning, right? When we were building out these billions and billions of apps. Sorry, I have to do the Carl Sagan thing. Well, there's like new things, of course, as we evolve. And this isn't a revolution, it's an evolution. One thing, networks have become a lot more ubiquitous, and the capacity is becoming more ubiquitous. That is, this is a picture of Starlink, which is going to put like 30,000 satellites in the air in low Earth orbit. This is a good example of like, well, now we have the potential, when Starlink finishes, we'll have the potential of having good quality, high-speed networking in any location on the planet mostly, except if you're in the North Pole or the South Pole. But that is the whole point of Starlink is network anywhere and high-speed network. And there are other networking, there's other companies that are doing it. Starlink is just one example. Amazon is doing this as well. I think there are a few others. But this is the future, and this is something we have to think about.
Hop online to InsideAnalysis.com for more information. That's where we'll post the archive. And folks, we want to know what you want to know. So if you have any thoughts about all this, send me an email, info@InsideAnalysis.com. That comes straight to me. And like I say, we're keen to understand what your impressions are. We want to know what you want to know. Send me an email, info@InsideAnalysis.com. With that, we're going to bid you farewell, folks. We'll talk to you next time. Take care. Bye-bye.